Hello, and welcome to a Reigate Maths video focusing on the graphs chapter of the first year Decision 1 unit from the A-Level Further Maths specification. My name is Simon, and in this video we're going to be focusing on some specific types of graph. If you haven't yet watched the videos introducing this topic and then the longer video on graph theory, I would advise you do that first, as we're going to be using some of the terminology that was introduced in those videos. The first thing we're going to do is introduce the names of some specific types of graph and then look at some examples of those. So the first specific type of graph we're going to look at is something called a tree. A tree is a connected graph with no cycles. So this first example here, so all three graphs on this right-hand side use the same vertices. This one is a tree because we get from A to B to C, but then we don't get back to A. Likewise, this one is also a tree, and this one is not a tree because we have the cycle A, B, C, A. Trees are by definition simple because as soon as you have multiple edges, so this for instance, we have a cycle, A to C back to A. So trees must be simple. And as we've seen, they also must be connected. Now there is a specific type of tree that refers to a graph itself, and that's a spanning tree. This is a tree that is a subgraph of a larger graph, and it must contain all the vertices in the original graph. So if we have the graph here that looks a little bit like the Star Trek logo, graph ABCD, this is our graph. A spanning tree could be this. It contains all of the vertices from the original graph, but is also a tree because it's a connected graph with no cycles. Okay, ABCD, this graph here is a spanning tree of this graph here. The next specific type of graph is something called a complete graph, which is a connected graph. It is by definition simple, and it is the graph where every vertex is connected to every other vertex by a single arc. If n is the number of vertices, we use the notation Kn to be the complete graph with n vertices. Because it's simple, but every vertex is connected to every other vertex, the order of each vertex is n minus 1. So we can draw the complete graph K3. That's a triangle. We've already drawn it. It's this one. Okay, it's got 3 vertices, and every vertex is connected by a single arc to every other vertex. K4, we can draw in a bunch of different ways. The sort of arguably best way to draw it is in this orientation, because we don't have any arcs crossing each other except at a vertex. But we could draw it in this way. Where we have something like this, and we could draw it like that. This is less good. It's unclear what's happening at this point here, so it's less good to do that. Better in this case would be maybe to do something like this. K5, we can't avoid crossing things over, so we're going to have to do that. Okay. So we've got kind of an outside pentagon, and then every vertex connects to every other vertex. And we can see here we can't really draw this nicely without having things crossing over. That's actually an important property that you'll look at in the second year, something called planarity, which is about whether you can draw a particular graph without having lines cross over. The last term that's quite important, and we'll use this example here that we've drawn for K4 to describe it. And the term is isomorphic. Graphs are isomorphic if they display the same information but are drawn differently. These two graphs are isomorphic. They are effectively the same graph even if they don't look like it. Likewise, if we took out this arc here, and then drew it like that, this graph is isomorphic to the first one we drew. They show the same information, but are drawn in different ways. This is a really important property with graph theory broadly, because two people might draw graphs in different ways, but they show the same information. That is very, very relevant because you're showing the same information. Quite a few of the algorithms that you look at across the 2 years of the Decision 1 unit only work with complete graphs. So this idea of a complete graph, or being able to change the way you talk about a graph to make it complete, is very, very useful to make a lot of the algorithms that we're going to look at work. Not all of them require complete graphs to function, but quite a few of them do. But this idea of a simple graph and a complete graph and a tree is really useful. When we look at the next unit of algorithms on graphs, there are two major algorithms that look at finding not only a spanning tree, but the smallest or minimum spanning tree, which is a really, really useful thing to be able to do, not just in its own right, but also for quite a few other algorithms. It is a really important thing to be able to do. That's kind of a nice overview of specific types of graphs that you need to know about. Thank you for watching.